Hello, Mr. Aaron, Mr. Ryan, are you right? Yeah? What did we talk about yesterday?
About minimum genetic mutation.
Yeah, minimum genetic mutation.
Breakfast search.
We use the breakfast search to solve this problem, right? So the problem is that we given these genes, right? Gene string. The gene string, there are 4 types: A, C, G, T. A pair with T, C pair with G, right? And we also talk about why the gene is like that, right? So look, it's a double strand, right? Double strand. So look, if this side is A and the other side is T, if this side is G, the other side is C, right? So DNA is more robust, meaning that if one of them is missing, your body knows how to repair it, alright? So your DNA carries information, right? Carries information. It's a double strand, right? And each one has 4 types of gene. It's like binary, but it's 4. It carries the information, and DNA needs to copy it. And this is more like the checksum. Alright, so when it copies, it knows if this information is correct or not. Okay, and we're given this gene, right? And then we also given a list of the valid gene in a bank. So we call it bank of gene, right? Bank of gene. So we want to find out from the star gene, right? Star gene may not appear in the bank of gene, but it's valid, star gene. And when we apply the mutation, how many steps, the minimum number of steps to reach to the end gene, right? And then all the mutation needs to be in the bank of gene. So one mutation, for example, ACCT mutation, we talk about one mutation. Mutation, the opposite of immutable, right? Immutable can't change. Mutation means change, slight change. So we pick one gene and then we can change to other 3 types. For example, we pick this C. If we pick this C, right? So we have GAT. So we can change the second gene to all 3 other types. Okay. And we use the breakfast search because the breakfast search is suitable to find the minimum steps from the source to a destination in an undirected or directed unweighted graph. It has to be unweighted graph. Unweighted means that the cost between the nodes, the edges, are having the same weights. Because each mutation costs 1 step. It's all the same. So this is breakfast search, and because there are only a limited number of genes in the bank, so the time complexity for the breakfast search is OB, right? Because for each mutation, it has to be in the bank, right? This is the bounded breakfast search. So what's the other search algorithm? You know, not breakfast search. Depth search. Okay, so we can apply the depth search in this case. Right?
It's
because
more trickier.
It's more trickier. Yes, it's more trickier.
You might go to a different end.
Okay. So for example, the breakfast search, you know that we use the double NDQ, level by level, right? Level by level. So when we find the first node, we find it, which is the target, is the guarantees the shortest distance, right? Well, because you're just searching basically level by level. The first node, the target node you find, is the answer, the optimal, right? If it's the depth search, it does not guarantee the shortest. Look, if the destination is here and possibly another one here, right? Look, when you perform a depth search, you go this here, you find it, right? This node you find it, but this is not the optimum. This is not shortest. Here, this is the shortest. So in order to guarantee the shortest distance, we can do a brute force using the depth search. So basically we exhaust the search. We can exhaust all the paths, right? When we find this, we'll just remember it, but we are not returning because we haven't finished the whole tree, right? We just continue searching. And here we update the optimal, right? So basically depth search in this case is more like a brute force, right? Because we have to exhaust all the paths.
But when you're searching like that, if it does not, that's depth search.
Yeah, depth search. The thing here is that when we perform a depth search, usually we return, right? But here we're not returning because we are not sure if this is the optimum. Am I right? Yeah? So we can apply the depth search in this case, right? Because there's number of these limited genes in the bank. If there is no such limit, this to exhaust all the paths in this tree may take longer. Ideally, this is not a very good approach, but we're just showing you here today, okay, to give you an idea. So in the next lesson, we're going to revisit this using the iterative deep learning search, which is the combined with the depth limit search. Incrementally set the max depth for the depth search.
Why did you write IDF?
Iterative deepening search. It's like that. Okay, so let's start with the step 0. The maximum depth is the distance is 0. So we stop here. And then, okay, we don't find it. So let's increment the max step to 1. So we do a depth search. Okay, and we find it. Okay, if we don't find it, we increment the max steps to 2. So we do a depth search. We are not going because the depth is 2, maximum 2, and we go back. So depth limit search. What's depth limit search? We perform a depth search with a maximum depth. Okay, depth limit search is depth search plus with a depth limit. Okay, that's what it is. Okay, so we going to implement the depth search. So depth search usually we can use the recursion and non-recursion, right? The recursion is more easier to implement, am I right? Yeah, because the computer maintains the stack class. Okay. First of all, set the answer to infinity. Right? We haven't found it. Infinity. Define depth search. We want to have a star. We have n and current distance, current steps, and we need to have a table, hash table, to remember the nodes we have visited. Right? Yeah, because mutation, if A changes to T, T might change to A again. Right? A changes to C, C might change to A again. We don't want that. Right? We don't want that. If we don't remember the nodes we have seen, what could happen? If we're not remembering this,
There'll be explanation. Then we're working out the same thing all over again.
yeah,
And
the
it'll
problem
take
will
forever.
take forever. The problem will never end, right? Because you just walk here, walk there, forwards and backwards. Okay, so we need to remember. For example, we need to remember this. We remember this, then we're not coming back. Okay, we're not coming back. We're not coming back. If star equal n, right? So we have visited the destination n, right? So we need to remember the current distance, which is save the answer. We want to get the minimum, right? And then distance, and then return. Okay, you can return true to say okay to say we found it, and then okay. If not, if the current node is in the scene, right? Yeah, if we have seen this before, then we return false, right? Return false. This is the pattern, right? Every time we check if the thing is in the hash set, if it's visited before, then we return. You look at the things in the notebook. If it's not there, what do you want to do next?
Cross out.
Cross out to mark it down. Okay, so I put a 1 here because I have visited now, right? So here now look scene dot add s, right? And then I'm going to do the next one, the mutation, right? Mutation, mute in therefore type, yeah? ACGT.
What's mut?
Mutation stands for mutation. Okay, I'm just lazy.
Mutton.
Okay, lazy. What's mutton?
You know, sheep.
Oh, the meat, the mutton. Okay, yeah. Yeah, there are only 4 types, right? So we talk about how to do the mutation, right? AGCT. So we can check we can mutate every gene, right? So for I in range, the length of current, this is going through the index. And the next one, the neighbor, right? We want to mutate this position. Then we take all the character, all the genes before, and all the gene after, and then we need to mutate, right? So all the gene before is S up to I, plus current gene we mutate to mut, plus Si plus 1 to the n. Okay, and of course this name can't be the same as S, right? Because if it's the same thing, there's no mutation, right? Look, we're just iterating. Look, ACCT. For example, I want to mutate the second one. So the second one has 4 choices. ACGT. The original one is C, right? So we don't want to continue doing this, right? Because it's the same. So we cross out that one. So AGCT. Okay? And if name not equals the original, if there's no mutation, and then we need to depth search name and distance plus 1, right? We're doing one more mutation and then scene. At the end, we need to remove it from remove the S, right? So because the depth search, yeah, we have seen this before. We have seen this before, but when we visit this another path, we haven't seen this node before, so we have to unmark it. For the depth search, if you mark it, if you're traveling the tree using the depth search, if you mark it, you have to unmark it somewhere. Okay? And also we have to check if the neighbor is in a bank. Yeah, this is most important. I forgot this. Yeah, because the neighbor has to be the mutation has to be in a bank. This is one more criteria. And then we're doing the depth search and depth search. Okay, now time complexity and space complexity. For this one is a lot trickier because we got this the bank of gene criteria. If we don't have this criteria, what happens? How do we analyze the time complexity of depth search? We just check. Look, if this node, how many kids of it? Or if there are two, for example, if it's a binary tree, what's the time complexity of depth search on the binary tree? So is OBD. Okay, so we use this notation. B is the branching factor, D is the depth. Okay, branching factor. Look, branching factor 2, depth. Okay. Yeah, because for each node you have two choice, right? So it's 2 to the power of d, right? This is more general kind of the analysis of the depth search on the tree. But for this one, the tree, right? The tree, how many possibilities? If the size of gene is n, right? So for n, if a gene is n size, A, C, C, T, for example, if there are n characters here. So how many possibilities? For each one, for how many mutations? So I can pick n of them, right? I can pick n of them. Each one has 3 choice, right? Each one has 3 choice. Make sense? So it's 3 times n, right? 3 times n. So this is the branching factor. And the D, the depth is length of B, right? The length of B. So the bank, so is O3 times n to the power of the bank, right? This is branching factor. 3 to the power of n. 3 times n, right? Or n, right? We drop the constant, maybe. N to the power of B. B is not the branching factor or anything. It's the length of the genes in the bank, right? Because it gives you the valid mutation, okay? Yeah. For depth search, the space complexity is the maximum depth of the tree. If the distance, the maximum depth is d, then the space complexity is OD for the depth search. Okay. But for breadth search is determined by because we have to use the Q. Okay. Yes. Okay. So what have you learned today? What's the problem? What have you learned today? And that's it. Eric, you go first.
We learned about the same thing from yesterday, but depth search.
Yeah. So can you tell more about this depth search? I mean, why?
Well, we have this notebook, and so we don't do the same thing. So whenever and every so often we mark it, so we don't do it again.
Yeah.
And
mark it and don't do it again. Here, mark it, unmark it, right? Depth search, we check if it's marked before. If it's visited, return false, right? Yeah. And if we find this, then we update the shortest path, shortest distance. This is kind of brute force in a depth search manner. Okay. So it only works in this kind of particular problem if this tree is unbounded. Then this will take forever. The ultimate solution is breadth search we talked about yesterday, level by level, because it guarantees the minimum distance as long as we find it. Right. The first node, we find it in breadth search is the ultimate. In an unweighted graph, it doesn't matter if it's directed or unweighted. Okay, it has to be unweighted. Okay, it can be directed or undirected, but it has to be unweighted. Okay, make sense? Can you tell me what have you learned today? And
the same thing as yesterday.
What's the same thing?
About the gene.
Okay, so what's the problem and how do we solve it?
We use depth search.
What's depth search?
Going deep as it can.
Yes, going deeper as we can, yes. Okay, and how we usually implement the depth search?
We use it like brute forcing.
What's calling itself, yeah?
Recursion.
Recursion, Eric, look, yeah. Recursion, yeah, look, Eric, yeah. Yeah? Okay? Yeah, that's it for today. Bye-bye.
Bye.
Bye-bye.